Hello, everyone, and welcome to the IDS Vision channel. My name is Miriam, and I'm your host today. So just a few organizational points. Today, we are having 3 presentations. After each presentation, you will get the opportunity to ask your questions. So please feel free to type them in the Q&A section below, either in German or in English. For technical issues, you can use the chat and contact me directly. After our 3 presentations, we will then have some time for your questions. And today's session will be recorded, and so you can watch it afterwards on the IDS Vision channel. So it has been quite some time being live on air with the IDS Vision channel, so I'm really excited about today, and especially about today's topic, AI in farming and food processing. You know, I went to a special gymnasium with a focus subject on agriculture. It is really impressive to see what's changing in this sector with the trends like bio or new technologies. Isn't it great how AI can help ease the hard work everyone does in farming and food processing? So, we will introduce our first speaker now, Stefan Strelen, who founded Strelen Controls over 10 years ago. He will let you peek into an innovative technology in a sorting process and how AI can help with quality assurance. So let's have a look at tomatoes, almonds, and pretzels. Stefan, the stage is yours.
All right, thank you. Let me just switch my video on. I hope you can also see me and you can hear me.
Yes, great, thank you.
So now I have to, even more important, share my screen so that you can see my presentation. I hope you can all see an orange screen now with an owl on it.
Not yet.
Not yet?
Nope.
Now?
Looking good? Yes, now
Yeah.
we can see it. Thank
Great.
you.
Thank you. So, good afternoon. My name is Stefan Strelen, and for the next 20 minutes or so, I'm going to talk about innovations in the determination of food quality and the determination of quality of agricultural products. However, before talking about innovations, I would like to take a brief look on widely used standard solutions of today. Imagine you should distinguish ripe tomatoes from unripe ones. This is where the fact that tomatoes change their color when they ripen comes in handy. Here you see a picture of ripe tomatoes in red and unripe tomatoes in green, as you all very well know. Now you can create photos of these tomatoes and use an algorithm to determine the color of the pixels of these tomatoes represented on the photo, and then evaluate them. Of course, some of the pixels have undesired color values, like white color, there where the light is directly reflected. But these issues can become overcome by methods of optics or computer science. For instance, by use of simple imaging filters. This is an approach which is quite simple, but also quite suitable and pretty often used for many applications. So you can now distinguish between the green and the red products and know that these products are representing unripe or ripe tomatoes. However, there are applications where the simple approach reaches a limit. Imagine you want to distinguish between an almond and an almond shell, like shown in this picture here. If you look at the shell, you will notice that it has different colors and, above all, does not stand out very clearly from the almond core, from the almond itself. And if you further consider that the color of both the almond and its shell may very well change from product to product, it becomes even more complex and complicated. And in addition to that, you might also want to distinguish other foreign objects whose color may very well be similar to the color of the almond. Imagine stones, plastic parts of of a plant like a leaf or an insect or even wood. You will agree that here, this is a far more challenging and complex job than diverting green tomatoes from red ones. So this previously shown naive approach reaches a limit. And now I would like to present two very innovative solutions that will help you to solve your problem anyway. The first approach is called hyperspectral image processing, and the theory behind it is actually quite simple, at least at the first sight. If you look at one pixel taken with a normal color camera from the almond, you will see that this pixel here represents a color. In this case, a brown, or let's call it brownish color. However, if you look at this color from a physical point of view, you will see that this color is not just represented by a singular value, but by a complex spectrum. Also, we are not able to see this spectrum with our eyes. It is definitely there. And what you can see here is such a spectrum shown intensity values over wavelengths of the electromagnetic waves. Even so, we are not able to see this with our eyes. We have a very fortunate circumstance that these spectrums can be measured. And this gives us a process in where we are able to distinguish a brown of an almond from a brown of a shell, from a brown of a leaf, from a brown of a piece of wood. So by hyperspectral cameras, which are able to see far more in a brown than you can see in a normal color camera or even with your eyes, we can now equip a sorting machine with such a hyperspectral camera. And how this looks, I would like to show you in a very short movie. I hope this works. Yes. Here you see our prototype version of the sorting machine equipped with a hyperspectral image processing camera. Here you see the infeed. A conveyor takes in the almonds together with almond shells and quite a lot of undesired foreign bodies like wood or leaves or insects into the machine. So the mass flow is transported inside the machine, and here passing a light. In this case, it's a pretty bright light that delivers wavelengths of a very bright band, as we need to examine a wider range of wavelengths than in a regular camera. And also the camera you see here mounted on top, looking through the light onto the conveyor where the products are moved underneath the system. So here you see the products are passing by our camera. The camera takes in the image, and then a computer system calculates color spectrums of each pixel taken by the camera and getting a result by the time the product reaches the edge of the conveyor, where it then falls down, passing a row of blowing nozzles, and these nozzles are then able to be controlled by the computer, taking out all products that were identified previously as an undesired material, for instance, a shell. So you see the parts of shells or other undesired products being blown out and falling into a special vessel for scrap. Here you see the good products collected in a container. And this is here a short section taken in one of our first installations in a plant where actually almonds are being sorted out by this machine. So this is a technology suitable for quite many tasks in the area of food sorting or food quality determination. However, some problems can even not be solved with this technology. And this is what I'm going to show you now. I have here chosen an example from the fresh bakery industry, but the questions that apply here are applying to many very similar applications. So be it meat, fish, agriculture, confectionery, or some others. In the case of the products shown here, the color, of course, can very well be determined. Also, the shape varies a bit from the left product to the right ones. But the question is, does this really help us? Is a little darker pretzel the more beautiful one, or a little lighter pretzel? This question is not so easy to be answered because it's not a physical value that determines beauty or aesthetics or appetizing. This is something that can only be judged by the consumers, and it may even change over time, for example, as consumers' preferences change. So the question is, how can we automatically assess quality in such a case? And the answer is by use of artificial intelligence, or in this case here, deep learning. And this is where a very practical property of neural networks or deep learning comes into play. The property is that these methods are able to learn from examples. This means an experienced employee or person or engineer judges the quality of some of your products, of the examples, and then on basis of these samples and judgments, intelligence system, a neural network system, is being trained and learns in this way to judge in a way a human operator would judge. After this learning phase, the system has learned a similarity relationship and can now make judgments on its own. And again, I would like to show you an example of such a solution in a short video. So, here you see a test bench, whereas the previously shown video was an inline process. What I'm going to show you here is an offline process where samples taken from a production by random shall be examined and determined by an intelligent system. And before such a system is able to work, it needs to be installed or trained. And my colleague, Daniel, is now going to show how this is done. So before you start with evaluating the quality of a product, you need to define a inspection job. But even before you do this, you need to have a a kind of quality classes. If you imagine quality is nothing that you can measure like temperature or color, there are no physical dimensions that represent a quality. And for this reason, at the beginning of a judgment process or a judgment program, you need to define values that you want to use to judge on later. This sounds complicated, but in fact, it's quite simple. In this case, that Daniel, my colleague, is shown here, he defines 4 different degrees of quality. He names it easily 1, 2, 3, and 4. And he also dedicates some colors, because colors are always easy to understand for humans. So he gives the quality class 1, the color green, which means perfect quality. Then comes yellow, orange, and finally red, which means the worst of all of our qualities. So this was part 1 of the step in assigning a quality system, which was quite easy. And now comes the next step, which is the training or teaching phase. Here, as mentioned before, at the beginning of such a process, we need to show our AI system what we understand as quality. And what Daniel does here, he gives a sample of different kind of quality classes. For instance, this bread roll here is not so nice, so he assigns the quality class 4. The next one is a little nicer, he gets class 3. The next one is even nicer, class 2. And finally, a very nice product, which Daniel decides is the highest quality, class 1. Of course, in a real system, you need more than 4 samples. But let's say after showing the system 200, 300, or 400 samples or so, you can start the training, which means a neural network will get formed and trained. And after this, our system is independently able to make quality judgments, as Daniel is now going to show. He takes out of the production, let's say from the oven conveyor, a sample, puts it in our working bench, and asks the system to judge on the product's quality, which it does here. It is a very ugly product, as you can see, and the system tells this here is the worst quality, class 4. And in it, now I'm going to show you a nice product, which also gets judged by an AI system as the highest quality class, as you can see here. And in addition to this, our quality label tower not only determines the quality of the product, it also automatically creates a report. So with a solution like this, you are able to build up and operate a comprehensive quality documentation system. Yes. And with this, I would like to conclude my presentation with a picture of our quality tower. Thank you for your attention, and we'll be happy to answer any questions you might have.
Thank you very much for this very interesting talk. So now we are ready to answer your questions. Please feel free to type them in the Q&A section below. We will just wait for some minutes. Okay, there is a question. How many samples do you need to learn your deep learning model?
Yes, that's a very good question. And it's difficult to answer because it varies a bit on the application. However, you might have heard that for deep learning, very large numbers of samples are required, and this actually was true for the first deep learning systems that were introduced in the market. However, today this changed as the whole technology was progressing, and in today's world, a typical size is a few hundred samples.
Okay, thank you. There's another question in the chat. Is the processing of the image done in the camera or on a separate IPC?
Yeah, thanks. Very good question. And the answer is quite easy. Both is possible. You need to focus on a few questions before you design a solution. One question is, do you need a result in real time very quickly? How many time do you have? Is it a question of milliseconds? Is it a question of seconds? How complex are the products, are the pictures you need to process? And then you can decide whether it's possible to calculate the inference in the camera, or whether you need a stronger hardware support, and then you need to do it in a larger computer, eventually with support of hardware that is more effective to neural networks like graphic processors. So the question is, it depends. It may be both. We have done installations where we apply neural networks in cameras directly, but it could also be in very, very powerful workstations.
Thank you. The next question, does your deep learning use color information from a hyperspectral camera?
That's also a very good question, because this would be then the final, most challenging task, to apply deep learning to images from hyperspectral cameras. I think basically it's possible, but so far we has not done this yet. Also, I also must say that even the classification in the application shown at the beginning, the nut sorting process, there also is a machine learning method used in the process of doing the classification of the individual pixels. So this also is a bit challenging. Yet this was not a deep learning, but another machine learning application.
Okay, thank you so much. And the next question. Are hyperspectral cameras special cameras, or is it the process itself that can process the pixel of a normal color camera?
Unfortunately, these are special cameras, because you need to be able to work with many bands of your color spectrum parallel. This is quite a demanding and complex application, and these cameras are really special cameras. They are bigger than typical color cameras. They are definitely more expensive. Yes, unfortunately, they are very special and very sophisticated.
And the following question, which hyperspectral camera do you use with the nut sorter?
It's a manufacturer called Specim. It's a manufacturer from Finland, and we use these cameras specifically when sorting food products or other products as well, because we're not only active in the business of food sortings, also other applications like rubber, for instance.
Okay. Seems like there's another one. How fast can your nut sorting application run?
The video you saw was real time. This is the speed that we are able to process at this time. So the machine that was shown here had a bandwidth of 450 millimeters, and this machine is able to process 1 ton of nuts per hour. I'm aware that conventional methods of sorting are faster, and we are working on this. If you if you double the width, for instance, you can get in the range of 2 tons per hour. But this is what we are able to do now, today, with one machine. So the speed is definitely not so bad, but it's slower compared to other technologies. This I have to admit.
How accurate is the quality classification?
Yeah, it's very accurate. The sorting process actually depends more on the precision of the nozzles, of the feeding, of the conveyor. The image processing itself is very, very effective and precise, and especially and you also you can design it or increase the result. For instance, if you have materials that are difficult to determine in the visual spectrum of the light, you can even move ahead the visual spectrum and also take near infrared wavelengths into consideration. So you are really able to distinguish many kinds of chemical or biological components. This is a very powerful and very precise technology. However, installations get also more and more complex and large, and unfortunately also a bit of expensive. But yes, it's definitely able to distinguish many objects very precise. Yeah.
Okay, and one last question for now. What communication protocol is used in the almond machine example between machine and vision system?
Actually, this is, I mean, we consider this is one system, and there was an image processing computer, and I think I'm right. The PLC for the real-time control. I'm not 100% sure, but I think it was real-time TCP/IP. It was nothing too sophisticated or special.
Okay, great. Thank you very much, Stefan. If you guys have any more questions, we will answer them afterwards because we have to go on with our second guest now. So thank you once again.